Welcome to today's session. So today's session is about binary heap in programming and data structures. So in this topic, you're going to learn what is binary heap, what are the operations in binary heap, and how to insert the values in a binary heap. And finally, you're going to discuss some gate questions also. So first, what is meant by binary heap? So binary heap is nothing but it is a complete binary tree. So what is binary tree? It is a tree in which a node can have at most two children. So heap is a complete binary tree which has at most two children. And the meaning of complete binary tree is the leaf node should be completely filled and all the nodes should be left justified. So that is the concept of complete binary tree. Leaf node should be completely filled and the nodes should be just left justified as shown in the figure. And this binary heap has some properties. So two properties I have listed out here. One is binary heap is a complete binary tree. And the second property is binary heap is either min heap or max heap. There are two things you have. One is min heap and another one is max heap. So what is meant by min heap? In min heap concept, the key value at the root node must be minimum when compared to all the other keys present in the binary heap. The key in the root should be minimum. Such heap structure is called as min heap. See this diagram. See here we have a complete binary tree where we have values in each node. The root node is having the minimum value. In this node, see this structure. So here the root node, that means the parent node will be having less value than the children. So such structure is called as min heap. Next one is max heap. In max heap, the value of the parent node is greater than its children. It's either greater than or equal to its children. So such structure is called as max heap. So in this diagram, the parent node is having greater value than the children. So when you see this particular substructure, so we are having value 9 in the root node when compared to its children 5 and 4. So likewise, in each case, the parent node will be having greater value. Such heap structure is called as max heap. Now let's see how this binary heap can be represented. We know that binary heap is a complete binary tree. So we can represent it in the form of array, where always in an array, the root element will be stored in the first position. That means at array of 0. So ARR of 0 will return the root element. AR of I minus 1 by 2 returns the parent node. Then we have to move to the left node and right node. For left node, AR of 2 asterisk I plus 1 and AR of 2 asterisk I plus 2 returns the right child node. See this diagram? Here, this is a binary heap. We are going to represent this in the form of array. Yes. So here we know that array will be represented starting with positions 0. So 0, 1, 2, 3, 4, 5. So at 0th position, we are having the value 1. So we have to put 1 here. At position 1, we are having the value 3. So at index position 1, we are having the value 3. Next, at index position 2, we are having the value 6. At index position 3, we are having the value 5. See here, at index position 3, we are having the value 5. So likewise, the values in the node will be represented in array format. Next, we will see the operations on min heap. So what are the operations we can perform in the heap? We can get the minimum value, we can decrease the key value, we can insert, all those operations we will be able to perform. So first operation is get min operation. So get min operation will return the root element of the min heap, because in min heap structure the root element will have the minimum value. So when you give get min function, it will return the root element, and the time complexity of this get min operation is order of 1. Next one is extract min. So extract min is going to remove the minimum element from the min heap, because in min heap when you give extract min, it is going to remove minimum element, and the time complexity is order of log n. The third operation is decrease key. So when you use this decrease key operation, it will decrease the value of key. If the decreased key value of a node, suppose if it is greater than the parent value, means then we don't want to do anything. Otherwise, what we have to do, we need to traverse through that structure, heap structure, in order to maintain the heap property. And the time complexity of this operation is order of log n. Clear? Next operation is insert operation. So insert operation will allow us to insert new key value. Whenever you want to insert a new key value, we have to use insert method. And the time complexity is order of log n. So when you add a new key value, always the new value will be added at the end of the tree. And afterwards, we have to check whether the entered value is greater than its parent or not. Suppose if it doesn't follow the heap property, then we need to traverse it and you have to fix it. Similarly, delete. So when you give delete method, it will delete the key value. And as like insert operation, delete also will take order of log n time. And when you delete a key value, at that case also we have to check whether minimum value is maintained in the root or not. Okay, so for extracting the minimum value which is present in the root node, what method we have to use? We have to use extract min method. And next we will move on to the heap operations. That means how to maintain the heap structure and how to insert an element, how to delete an element. All those things we are going to discuss now. The first one is heapify. Heapify means it is a process of creating a heap data structure. From the binary tree, we are going to construct binary heap. So already we discussed about trees, binary search tree, all those things. So from the binary tree, we are going to construct heap data structure, and that process is called as heapify. And the use of this heapify function is to create either min heap structure or max heap structure. Now let's see an input array. We know that heap structure can be represented in the form of array. So the array of elements is given. From the array of elements, we are going to construct a heap data structure. Clear? So here this is an input array having some values here, and the index positions of the array is also represented. At 0th position we are having the value 3. At first position we are having the value 9. At second position we are having the value 2. And at position 3 we are having the value 1. and at position 4 we are having the value 4, and at position 5 we are having the value. So using these values we are going to construct a heap data structure. Yes. See, this is a complete binary tree. From the array we have created this. This forms a complete binary tree. So what is complete binary tree? We should have at most 2 children, and heap is a complete binary tree. So we created a heap data structure here. See, always we have to start from the first index of the leaf node. See here. So when you construct a heap structure, we have to maintain the heap property. What is the heap property? Either we have to maintain min heap property or max heap property. Min heap property means the minimum value should be at the root node. Max heap property, maximum value should be at the root and parent node. In such a way we have to maintain. Now let's see how to insert elements into a heap. For that, an algorithm is given. So first, suppose initially if there is no node already, we have to create a new node. If there is node already present means we have to create the new node at the end, because already the tree is there. So we have to insert a new node at the end. And afterwards, we have to heapify the array. Heapify the array means we have to fix the heap property there, either min heap or max heap. As such, it is not possible for us to insert the values. We have to insert the new node at the end, and we have to check whether it is satisfying the heap property. So this is the algorithm for inserting element in a max heap. See, we have a heap structure here. We are going to insert a new element or new node, which is nothing but 7. So already we are having some 6 values: 9, 4, 5, 1, 3 and 2. Now you are going to insert a new node having a value 7. So as I said earlier, the new node should be added at the end as the last node, because already there are some nodes available here. So always you need to insert a new element at the end of the tree. After inserting, we have to heapify the tree. What is the meaning of heapify the tree? You have to traverse in such a way that it should maintain the heap structure, either min heap or max heap. So we have inserted 7 at the last. So here this is about inserting element in a max heap. What is the meaning of max heap? The parent node should have a greater value than the child. So in the previous slide, we have seen that the value 5 is at the parent node and 7 is at the child node. So what we need to do? We need to heapify. For heapify, we have to move 7 to the parent node and bring 5 to the child node. So when you see now, all the parent nodes are having a greater value than the child node. Thus, it maintains max heap property. Next, let's see how to delete element from the heap. So, first we have to check which element or which node you are going to remove. Whether the node that you are going to delete is a leaf node, or whether the node that we are going to delete is the last node, or whether it is a root node or a parent node. All those things, you have to check it first. Suppose if the node that you are going to delete is the leaf node, means you need to remove that node. Else, Suppose some parent in between nodes, if you are going to delete, means you have to swap that node with the last leaf node. If it is leaf node, it's no issue. Directly you can remove it. Suppose the node that you are going to delete is not the leaf node. It is some internal nodes. Some parent nodes you are going to delete, means you have to swap that node that you are going to delete with the last leaf node. And then you have to remove that node. And also you have to maintain the heap property. This is the algorithm for deletion of node in a max heap. Now we will see the example for this. See here, this is a heap structure. So here I'm having a value 3. This 3 I am going to delete. So if suppose this 3 is a leaf node, means I can remove directly. I don't want to do any swapping process. But here 3 is an internal node. It is a parent of 1 and 4 these nodes, right? So what you have to do? You have to swap this node 3 that you want to delete with the leaf last node. Which is the last node? This one, 5. So you have to swap it. So that we will see in the next slide. See, I have swapped 3 to this position 6, and here already I'm having a value 5 no in 6th position, that I swap to the first position. Now the node that I want to delete is what? 3, which is the last element, correct? I can delete it. So I can remove this element. Now we will see. After removing it, what is the next step? We have to heapify the tree and check whether it is maintaining the max property. Yes, it's maintaining. See, the parent nodes are having the greater value than the children. Suppose if the parent is not having greater value, if it is having less value, means you have to traverse and swap so that the parent should have greater value. Parent nodes and also the root node should have a greater value than the children. In such a way, you have to heapify the tree. And next we will see the applications of heap data structure. In where and all we can use this heap. So binary heap can be used when you implement priority queue. And also it is mainly used in Dijistra's algorithm and also in heap sorting. So in sorting technique, we have a concept called heap sort. In such place, the heap data structure is used. So these are the main applications where we can use heap data structure in priority queue implementation, in Dijistra's algorithm, and also in heap sorting. And now that's all about the theory part of binary heap. Now we are going to discuss some of the gate questions. Yes? Yeah. See this graph? A graph is given here. You have to identify the curved vertices. So which are the vertices here? A, B, C, D and E. So vertices are nothing but what? The nodes of a graph. Okay. So in tree we used to call it as nodes. In graph we used to call it as vertices. Yes. So vertices and nodes are going to give the same meaning. So in this given graph, you need to identify the cut vertices. So what is the meaning of cut vertices? So when you remove any vertex in a graph, the remaining graph will be in a disconnected form. So when you remove which nodes or which vertices, the graph will be like disconnected in a collapsed manner. That we have to find it. So that's the question. Yes. So the first option given is B and E. See here, B and E. B is going to be the last, right? So when you remove the last, it doesn't affect the remaining part. Only when you remove some internal nodes, it will affect the entire graph structure, right? So therefore, the main thing here is when you remove either B or C, then the graph becomes disconnected. So which are the vertices in this graph? B or C, B and C. So when you remove C and when you remove A, the graph will become disconnected. So the option is D option. What's the D option? The answer is B and C. Yes. Now we will move to the next question. See, here also a graph is given. We have to find which are all the given statements is true. Yes. The first option given is this graph G is a complete graph. That is the first question. Second option is G is not a connected graph. Third option is the vertex connectivity of the graph is 2. And the fourth option, the edge connectivity of the graph is 1. So 4 options are given. You have to find which are the options are true. Yes. So find out. What is this option 3 and 4? That is option C and option D. The vertex connectivity of the graph is 2, edge connectivity of a graph is 1, all those things. So vertex connectivity, it is related to the connected graph. So when you remove any vertex, the graph will become disconnected. So when you remove some nodes or some vertices in this graph, see, for example, when you remove this vertex B, and also when you remove this vertex C, the graph will become disconnected, right? So therefore, which statement is true among all these 4 options? Third option. So what is the third option? The vertex connectivity of a graph is 2. Yes. And here the first option is not correct because it is not a complete graph. Yes. Second is also not correct. G is not a connected graph. See here there is no connection between D and E. If all the nodes in a graph or all the vertices in a graph are connected, then it is called as a connected graph. That we discussed in the previous session, right? Yes. Now we will move to the next slide. A graph is given and they have given the question as the graph is a regular graph. We have to find whether that statement is true or false, whether the given graph is regular graph or not. See, what is the meaning of regular graph? The degrees of all the vertices are equal. Yes. What is the meaning of degree? What is the meaning of degree? See here. Consider the vertex A. So from A, you have a connection to B, C, F. Yes. What is the value? 3, no. So consider another one vertex. Let me come with this D vertex. So here we have C, then E and also F. So here also the degree is 3. So when you check this graph, the degree of all the vertices are equal and also every vertex the degree is 3. Is it not? So therefore the graph is a regular graph. So the answer for this is true. So the given graph is a regular graph. Now we will move to the next one. A graph with all vertices having equal edge is known as dash. You have to find the graph with all the vertices having equal degree is known as dash. It's very easy question. In the previous slide itself, we came across the same thing, right? A graph is given. We found the degree of each vertex. Is it not? So when you in that graph, the degree of all the vertex are same. Yes, no? 3. The answer is 3 for all the vertex. So when a graph having all vertices equal degree, then that graph is called what? Whether it is multi-graph or regular graph or symbol graph or complete graph. It is called as regular graph. So the graph is regular when all vertices have equal degree. So option B is the right answer. Now we will move to the next slide. See, let G be a weighted graph with H weights greater than 1 and G dash be a graph constructed by squaring the weights of edges in G. Let T and T dash be the minimum spanning trees of G and G dash respectively with total weights T and T dash. Which of the following statements is true? That you have to find. So, which are all the graph given? Two graph, that is, first a graph G is given and it is a weighted graph. What is the meaning of weighted graph? A graph having weights on the edge. That is nothing but the cost that is needed for traversing from one node to another, and that positive value will be indicated above the edge and it is called as the weight. So such graph is called as what? Weighted graph. So G be a weighted graph with edge weights greater than 1. So the weight of each edge is greater than 1. The value 1. It's greater than 1, that's given here. And another graph is constructed and the name of the graph is represented as G dash. And how it is constructed? It is constructed by squaring the weights of edges that is present in the already existing graph called G. And what is the value? All the weights are greater than 1. Now we need to find the weights of this G dash. You need to construct a graph in such a way that how? By squaring the weights of edges. And from that graph G and G dash, a minimum spanning tree is constructed and that is represented as T and T dash. And the total weights as small t and small t dash. And the statements which is true that we need to find. That's the question. So first option is T dash equal T with total weight T dash equal T square. So T dash, capital T dash and capital T represents the minimum spanning tree and small t dash represents the total weights. Clear? So first option is T dash equal T with total weight T dash is equal to T square. Second option, T dash equal T with total weight T dash, that is small t dash, less than T square. Third option, T dash equal not T but total weight T dash equal T square. And the fourth option, none of these. We know that the second graph G dash is constructed by squaring the weights of edges in G, right? So definitely T dash will have a weight of square and it will be greater than the weight of small t. Why? Already in the question it is given the edge weights are greater than 1. Yes. So therefore among the four options, when you see the second option, it is T dash equal T. Yes, we have constructed the minimum spanning tree T and T dash. No. So T dash equal T with total weight small t dash less than small t square. So option B is the right answer. Now we will move to the next question. What is the worst case complexity of inserting n square elements into an AVL tree with n elements initially? So what is tree? Tree is a group of or collection of nodes. Is having root node, parent node and other children's can have. In that we will be having so many trees: binary tree, then binary search tree, AVL tree, etc. So here we are going to discuss a question which is based on AVL tree. What you need to find? We need to find the worst case complexity of inserting n square elements into a AVL tree with n elements initially. What is the time complexity? Whether it is order of n square or order of n square log n, order of n power 4, order of n power 3. Which will be the option? We are going to insert n square elements. We always used to say the time complexity will be of the form log n, order of log n. So when you want to insert an element, it takes the time complexity order of log n. Here we are going to insert n square elements into an AVL tree. Initially we are having n elements there and you are going to insert n square elements. So definitely the worst case time complexity will be order of n square log n. So the option is B option. Second one is the right answer. Order of n square log n. Now we will move to the next question. Consider a binary tree that has 200 leaf nodes. Then the number of nodes in T that have exactly 2 children are. So we know that binary tree is going to have a minimum 2 children. Binary means 2 values. So 2 children will be present for each node. So here the number of leaf node in a binary tree T is 200. So 200 leaf nodes are there. And you need to find the number of nodes in the tree which is having exactly 2 children. So when you consider a root node, it has 2 children. When you consider the next node, again it has 2 children. So likewise, you have to find the number of nodes that are having exactly 2 children. Among the 200 leaf nodes, how many nodes will have exactly 2 children? That we have to find. It's a very easy question, right? So when you see that, what will be the number of nodes having exactly 2 children? 199 leaf nodes. Okay, so the right answer is 199. Among 200 leaf nodes in a binary tree, the number of nodes that have exactly 2 children is 199. Yes. So that's all about for today's session. If you have any doubt, you can ask now. Students, if you have any doubt, you can ask now. So no doubt. So hope you enjoyed the class. Thank you all. We will meet in the next session.